Welcome to part 2 of lecture 4. We're going to now talk about linear congruential generators. What this is actually going to produce is a sequence of integers. And I want you to note that this is not yet what we just defined as a random number. Remember, a random number within our definition is a uniform 0, 1 variable. Okay, so it's not quite that yet, but we'll show how to easily convert it into that. However, this is the first step. And what I'm about to show you is actually a very old method of random number generation, and it still sits at the heart of most modern random number generators. So although it's not quite what like a program like Simio uses, it is the subroutine the algorithm they do uses. Okay. So the idea here is that we are going to have a integer. We call this our seed. And then we're going to generate a stream of integers from this. Using the following recursion, we're going to say, given that you have a number, x sub I, so this x sub I you should think of as the input, the multiplier, the increment, and the modulus, which we call a for the multiplier, c for the increment, and m for the modulus. These are all fixed constants. And then the next iterate is generated from the previous one by the following formula. You multiply the current iterate x sub I by a, you add c to it, you add the increment, and then you take the modulus, which remember is the remainder function. Okay, so it means you divide by m and take whatever remainder is there, and that's the next number. Okay, so let's see how this works in an example. So for the modulus, n mod m is the remainder of n divided by m. So 14 mod 5, well, what is that equal to? 14 divided by 5 is 2 with a remainder of 4. So 14 mod 5 equals 4. Okay. So maybe in a couple other examples, 12 mod 6 is equal to 0, because if you divide 12 by 6, you get 2 with a remainder of 0, so it's 0. If you take, say, 115 mod 60, well, what is that? That's going to be 55, because the remainder is 55 when you divide by 60. And I use 60 on purpose because this is a kind of modulus that we compute all the time. You can think of this as a clock time. Okay, so we use modulus quite a bit, actually. We use them often with time. 7 days a week, 24 hours in a day, 60 minutes to an hour, and so on and so forth. So, as I said before, the initial value x0 is called the seed, and this actually controls the random stream we're going to achieve from this. Because if you start from the same seed, you get the same sequence of pseudo-random numbers. Note that the minimum possible value of this is going to be 0, and the maximum is m minus 1. Remember, the remainders cannot be bigger. It can be at most 1 less than the multiplier. If we have what's called a multiplicative congruential generator, that just means there's no increment. In other words, c is set to 0. And if we have a mixed congruential generator, it means that it's not equal to 0. So let's see how this works. So suppose we had a modulus 16, increment 11, and multiplier 9, and we're going to calculate the next two numbers in the sequence produced by the LCG with a seed value of 2. So x0 here will be equal to 2. Okay. So we start with x0 equal to 2. x1, according to our formula, is going to be 9 times x0 plus 11 mod 16. Okay, so we substitute in the 2 for x0. If we multiply that out, it's 18 plus 11. So that equals 29. Mod 16 is 13. Okay. So note that 16 goes into 29 once with a remainder of 13, so x1 is now 13. Okay. Now to compute x2, we apply the same formula except now with x1 in the place of x0. And this, of course, is going to be 9 times 13 plus 11 mod 16. Pushing that calculation through, we get 100. 9 times 13 is 117. Plus 11 will be 128 mod 16. And 128 mod 16 is 0, because that goes in evenly. Okay, we can do more. I'll do one more just for fun. x3 equals 9 times x2 plus 11 mod 16. That equals 9 times 0 plus 11 mod 16. Of course, this just equals 11. Because 9 times 0 is 0, plus 11 is 11. 11 divided by 16 is 0, with a remainder of 11. Okay, so how are we going to turn this into random numbers, right? This is not random numbers yet. Well, all we do is we divide by the modulus, taking advantage of the fact that the xi, remember, is greater or equal to 0 and less than or equal to m minus 1. For a big enough modulus, this is going to start to look like a uniform random number. Often we use a modulus that's a power of 2 because a computer uses binary computation. This helps the efficiency. So consider the LCG with modulus 16, increment 11, multiplier 9. Remember, we calculated the first three numbers. They were 2, 13, and 0. And indeed, x3 was equal to 11. And then if we want to turn them into random numbers, well, what would we get? We're going to divide this, each of these, by 16. Right? So the random number, R0, here is 2 sixteenths, 13 sixteenths. And for x3, which was equal to 11, the random number 3 was equal to 11 sixteenths. So how do we know if this works? It turns out there's a very nice theorem that lets us know. In fact, it gives us the exact conditions we need to have the full period. In other words, if you think about how many numbers can occur in such a pseudo-random number generator before repetition, the maximum number is m, right? Because it has to assume all the values from 0 up to m minus 1 before there's a repetition. This would be the ideal case. Is that we would have this occur. This is the best possible case. So this occurs if and only if these three conditions. So this best case, it occurs if and only if conditions 1, 2, and 3 occur. That is the very best case that can happen. Okay. And what is that? Those three conditions. C and M have to be relatively prime, which means that the only thing that divides them are 1. That's common to both. If M is a multiple of 4, then A minus 1 is a multiple of 4. And then if P is a prime number dividing M, then A minus 1 is a multiple of P. So these are seemingly weird and random conditions, but it turns out they're what's required. This is, if you ever take number theory or study any number theory, this is a number theoretic result. So let's see. Does this LCG have have a full period? And the answer is indeed it does. The factors of C are 1 and 11. the factors of M are 1, 2, 4, 8, and 16. So their greatest common factor is 1, so that's relatively prime. We have 16 is divisible by 4. Okay, so if that's true, it must be the case. So M is divisible by 4. We can write M divides 16. But then it turns out that A minus 1 is also divisible by 4, so that's good. Note the if-then quality of that. If 16 had not been divisible by 4, then that condition would be trivially satisfied. And then we have that the prime divisors of 16 are 1 and 2, and then we also have that A minus 1 has the same prime divisors. It's divisible by both 1 and 2. So we look back at our theorem. So we have if P is dividing M, then A minus 1 is also a multiple of P. So we have our condition. And indeed, if you want to check this, you can also check this computationally if you wish. I mean, the theorem says it's true, but we haven't shown you the proof, so you might be wondering, is it really true? And you can use a spreadsheet. And what you'll see is that you're going to get 16 different integers before there's a repetition, no matter what seed you start off with. I'll note that because C is equal to 11, this is a mixed LCG. Okay, I'm going to stop there.